Greedy technique. I'm Efina and I'll be presenting you this topic. The topic of discussion in this presentation are what is a greedy technique and two example algorithms that uses greedy technique, which are the Prim's algorithm and the Kruskal's algorithm. Greedy technique. The central point of greedy technique is that the choice made at any instance in solving the problem must follow the following three criteria. First one, the solution to the sub-instances must be feasible. That is, it has to satisfy the problem's constraints. Second one, the solution must be locally optimal. That is, it has to be the best choice among all feasible choices available at that instance. The last one, the solution is irrevocable. That is, once made, the solution cannot be changed on subsequent instances of the algorithm. Prim's algorithm. The problem for which the Prim's algorithm finds a solution is, given endpoints, connect them in the cheapest possible ways so that there will be a path between every pair of points. In Prim's algorithm, the points are represented by the vertices of an undirected graph, and the possible connections by the graph's edges and the connection caused by the edge weights. Prim's algorithm finds the minimum spanning tree of such a graph. So what is a spanning tree? A spanning tree of an undirected connected graph is its connected acyclic subgraph that contain all the vertices of the graph. That is, a spanning tree of an undirected graph does not contain any cycles, but it contains all the vertices of the graph. Hence, the spanning tree of an undirected connected graph is a tree. So what is a minimum spanning tree? The minimum spanning tree is its spanning tree of the smallest weight, where the weight of the tree is defined as the sum of all its edges. So let us see how the Prim's algorithm finds the minimum spanning tree of a undirected connected graph. Prim's algorithm finds the minimum spanning tree of an undirected graph using greedy technique. In the example given here, Prim's algorithm builds the minimum spanning tree starting at vertex A. Prim's algorithm records the edge weight of all the vertices connected to A. And for all the vertices not connected to A, the edge weight is marked as infinite. The very first vertex, A, is included in the minimum spanning tree. The vertex A is connected to vertex B with the edge weight of 3, which is recorded. Vertex E is connected to A with the edge weight of 6, which is recorded. And similarly, vertex F is connected to vertex A with the edge weight of 5 and it is recorded. Vertex C and vertex D are not connected to vertex A, hence its edge weight is recorded as infinite. So the next node that is included in the minimum spanning tree is the vertex that has a minimum edge weight. So in the given set, B has a minimum edge weight of 3 and it is connected to the vertex included in the minimum spanning tree, which is A. Hence, The next vertex that is included in the minimum spanning tree is vertex B. And since B is also included in the minimum spanning tree, the algorithm proceeds by recording the minimum edge weights of adjacent vertices of the vertices included in the minimum spanning tree, and then including the vertex with the minimum edge weight to the minimum spanning tree. So, when B is included as a vertex in the minimum spanning tree, all its adjacency vertices which has the minimum edge weight is calculated and recorded. So now C is connected to B vertex with the edge weight of 1. D is not connected to any vertices, that is, it is not connected to either A or B that is included in the minimum spanning tree. E vertex, as before, is connected with the A vertex with the edge weight of 6. But now F vertex has a minimum edge weight when it is connected with B rather than it is connected with A. That is, with A, F has a edge weight of 5, but with B, F has a edge weight of 4. Hence, the minimum edge weight is recorded, which is 4. Now, of all the given minimum edge weights that is recorded, C has a minimum edge weight of its connection with the vertex B. Hence, B is included in the minimum spanning tree. Now, all the edge weights of adjacent vertices is checked again. Now, D is connected to vertex C with the edge weight of 6. E is connected with vertex A with the edge weight of 6, and F is connected with vertex B with the edge weight of 4. Now F has the minimum edge weight with its connection with the vertex B, which is already included in the minimum spanning tree. Hence, F is included in the minimum spanning tree. Now, the minimum edge weights of the adjacent vertices that are connected with the vertices included in the minimum spanning tree is recorded. Now D has an edge weight of 5 with its connection with F vertex, and E has a edge weight of 2 with its connection with the F vertex. E has the minimum edge weight. Hence, E is included next in the minimum spanning tree. Now, D has a edge weight of 5 with its connection with F. Now, the last node or vertex that is included in the minimum spanning tree is D. So, the connection between these vertices will give the minimum spanning tree by which all these vertices could be connected. The input to the Prim's algorithm is a weighted connected graph with a set of vertices and set of edges. The output of the Prim's algorithm is a set of edges composing the minimum spanning tree represented by the variable e suffix t. E suffix t is initialized to null. The variable v suffix t represent the set of visited vertices and it is initialized to v suffix 0, which will be the root of the minimum spanning tree. For all the vertices in the graph, for the vertex that is currently included as the visited vertex, find all the adjacent vertices that are connected to the currently visited vertex and find the minimum edge that connect these vertices. The minimum edge is represented by the set v asterisk u asterisk. V asterisk is the currently included vertex and u asterisk is the vertex to which it is connected with the minimum weight. The new visited vertex will be u asterisk and it is included in the set of visited vertices represented by the variable v suffix t. And the edge connecting them, which is e asterisk, is included as the edge in the minimum spanning tree. The algorithm returns the set of edges composing of the minimum spanning tree. The efficiency of Prim's algorithm depends on the data structure chosen to represent the graph. If a priority queue consists of the vertices in the graph that are not yet included in the minimum spanning tree, and it is built considering the vertex distances to the nearest minimum spanning tree node, then its root is the vertex with the minimum edge connecting to the node in the minimum spanning tree. Hence, it is deleted from the priority queue and included in the set of visited vertices in the minimum spanning tree. Deletion of the smallest element from the min heap of size n is big O of log n operations. If the graph is represented by adjacency list and the priority queue is implemented as the min heap, the time complexity of Prim's algorithm, considering modulo of E is the number of edges in the graph and modulo of V as number of vertices in the graph, then the time complexity is represented as big O of modulo of E log modulo of V. Kruskal's algorithm. The problem statement. Given endpoints, connect them in the cheapest possible way so that there will be a path between every pair of points. In Kruskal's algorithm, the points are represented by the vertices of an undirected graph and their possible connection by the graph edges and the connection caused by the edge weights. Kruskal algorithm, very similar to the Prim's algorithm, finds the minimum spanning tree of such a graph. The algorithm begins by sorting the graph edges in non-decreasing order of the weights. Then, starting with the empty subgraph, it scans the sorted list, adding the next edge to the list of current subgraph if such an inclusion does not create a cycle, and simply skipping the edge otherwise. Let me illustrate Kruskal's algorithm with an example. The graph given here is a undirected, connected and weighted graph with 6 vertices. Let me illustrate the Kruskal's algorithm with the help of a 3-column table. The first column in the table consists of the edge that is included in the minimum spanning tree. The second column consists of sorted list of edges based on the edge weight. And the third column consists of the illustration. When the edges are sorted based on the edge weight, the first edge is BC, which has an edge weight of 1. So the edge that is connected to the minimum spanning tree should not form a cycle as per Kruskal's algorithm. Including BC to the minimum spanning tree does not form a cycle, and it has the minimum edge weight, and hence it is included as an edge in the minimum spanning tree. The next edge in the sorted list of edges is EF, which has an edge weight of 2. Including EF in the minimum spanning tree also does not create a cycle. Hence, EF is included as the next edge in the minimum spanning tree. The edge AB with a edge weight of 3 is the next minimum, and it does not form a cycle with the edges included in the minimum spanning tree, and hence, as per the Kruskal's algorithm, it is included as the next edge in the minimum spanning tree. Similarly, the edge BF with the edge weight of 4 is included in the minimum spanning tree, since it does not form a cycle with the edges that are already included in the minimum spanning tree. The edges CF and AF next in the sorted order forms cycles. Hence, they are excluded from the set of edges in the minimum spanning tree. The next edge that is included in the minimum spanning tree is the edge DF with the edge weight of 5. Now, all the vertices in the graph are included in the minimum spanning tree with a minimum edge weight. Kruskal's algorithm is implemented as disjoint subsets and union and find algorithm. A collection of disjoint subsets of a finite set with the following operation helps to implement the Kruskal's algorithm. The operation makes it create a one-element set representing the edges of the graph. The operation find returns the subset containing the minimum edge weight. The operation union constructs the union of the disjoint subsets S suffix x and S suffix y. S suffix x represents the edges included to the minimum spanning tree, and S suffix y represents the edges not yet included in the minimum spanning tree. When an edge from S suffix y is minimum, and when it does not form a cycle with the edges included in S suffix x, then after its inclusion to the subset S suffix x, it is excluded from the subset S suffix y. The most complex operation in Kruskal algorithm is the find operation. Hence, if the graph edges are represented as a linked list, then the time complexity of Kruskal's algorithm is big O of n. And if the graph edges are represented as a tree data structure, then the time complexity of the Kruskal's algorithm is big O of log n. To summarize, in this presentation we discussed how greedy technique is used in Prim's and Kruskal's algorithm to find the minimum spanning tree in a undirected weighted graph. Thank you.